but it's what is required to get minerals into the plants. And we'll be talking about a little tiny bit about soils, because there's a soils course, of course, that you can have. And we're going to be concentrating more how things move in through the membranes. And we'll finish up with just a little bit about mycorrhizae, whether or not there's a lot of newer data that indicates that, you know, most of the older data with mycorrhizae was basically just made up. So we'll talk a little bit about soils. And, you know, one thing that you understand very quickly is that the kind of soil that is surrounding the plant root is probably paramount in terms of what is going to get into the plant. And this is not just how fast or how easy that iron can be absorbed or any other mineral can be absorbed. It's going to be how the soil handles water more than anything. If you have the typical stuff I have in my backyard, then I'm dealing with clay. And though you can talk about, you know, cations and ions and whatever, with clay, really we're dealing with a type of soil that really restricts oxygen in the soil. And I remember my first year here, there had not been any rain for the entire summer, and I moved into the house that I'm in now in August. And so I tried to put a garden out behind my house. I put a garden out behind my house, and then it rained every day for 6 weeks. And if it's a clay soil, you know, there's really not much open aeration in a clay soil. And I could go out and I could just take a shovel and I could just, you know, stick the shovel into the ground and see it undulate out, you know, because the clay was basically at its maximum concentration of water, which meant very little oxygen. No minerals are being taken up by the plants. Doesn't matter anything else. With the rain, the consistent daily rain, the high water, the low oxygen really cuts off most uptake of minerals into the soils. So even if you have a soil that's great, if you've got rain every day and the water potential of the soil is zero, what you're going to get after a short period of time is a lot of roots that are going to become damaged because they're not producing ATP. And when we talk about metabolism, we'll talk about ATP, but these things are all wrapped up together. And so you've probably heard of micelles, or that organic material can add humus, which is good. And the point of this little graph here is to show you that this looks pretty doubting in terms of mineral uptake, but basically what you've got is that same cubic amount of particles, but that roots can actually sometimes grow between the particles. So, depending upon the kind of soil, the roots, the purpose of the roots, of course, is to increase the surface area for mineral uptake or water uptake. And you may even see sometimes some roots grown under different conditions will look differently. You know, some roots, if you grow them under very poor nutrient, in a poor nutrient environment, the roots will become a lot finer because they're trying to mine that much more soil area for minerals. So now let's talk about those roots, and let's talk about a root that's okay. It's got producing ATP. It's not been flooded for a month. And we've already talked about these kinds of mechanisms, which are at the bottom there, that sometimes minerals move by simple diffusion. What does that mean? What is simple diffusion?
Yeah, it's going from
Higher, lower, membrane's not involved. It just moves from higher concentration to lower concentration. Then we have facilitated or facultative diffusion, which is a protein's involved in this. Okay? No energy is needed, not from an exact mechanistic standpoint. And then at the bottom there we have active transport. And to put active transport, draw a line out by that and put ATP hydrolysis. That active transport, 99.99 times out of 100, means for that overall mineral, ion, whatever the heck you want to call it, that its movement is dependent upon the hydrolysis of ATP. And that energy of hydrolysis grabs that mineral and moves it across in some way, shape, or form. Okay? And this goes back to when we were talking about cell membranes. And you may remember seeing this. So we have simple diffusion. We have more molecules on the outside than the inside, and so they just move through in a concentration gradient. Now, this is simple diffusion. So if I have 10 molecules on the outside and 1 molecule on the inside, that 1 molecule on the inside is going to diffuse out, and those 10 molecules are going to diffuse in. So just by random motion, just by Brownian motion, you're going to get molecules inside, right? Until you start with 10 on the outside, and let's say none on the inside, you're going to end up with 5 on the inside and 5 on the outside, theoretically. No, they're just moving across. The movement of 1 molecule across does not have a direct effect on the movement of the exact same molecule the other way. It's just random. Okay? Now, there are 2 other forms of passive diffusion. Why is it called passive diffusion? I just told you. Why does it mean, what does passive mean? No ATP burns. And you're going to see, starting with Wednesday's lecture, maybe Wednesday's lecture, that ATP moves everything around the cell. So we have these 2 mechanisms. We have a channel protein, which I think I showed you aquaporin, which was a gated channel. And in this case, an aquaporin, what does that remove? What does that move? Water. Actually moves water. It's amazing. Moves water through the membrane faster than water can move through the membrane. And then we have this other class of facilitated or facultative diffusion called using a more of a carrier protein. Now, channel protein basically means if you look down the y-axis, you can see a hole in it. And that channel can be modulated. And I think in the last lecture I showed you an aquaporin and the way the side groups of amino acids helps grab the water molecule and move it through the channel. So it's like a hole. If you look out, if you stand outside the membrane, you can see inside. It may not be like a simple hole, but if you could move around, you'd be able to see there's a hole from the outside to the inside. Then with carrier proteins, there's not necessarily a hole through the membrane. There is a mechanism, and think about back to the three-dimensional shape of proteins, where you have this charge on the outside that grabs that molecule of choice and starts pulling it in from the outside. The next side group, or combination of side groups, grab it, pull it down a little bit more, and over and over and over and over again, to where just the attraction and the way these attractions can continue moves something from the outside to the inside. And that's facultative diffusion. Then we can talk about the last one, which in this case, this requires ATP. So the energy when ATP is hydrolyzed there is energy produced from that reaction, and that energy is used to drive the movement of the molecule, okay? Or the mineral, or whatever it is. Questions? Yes, sir.
Channel protein, is it door always open, or does it have the ability to open and close?
Good question. The channel protein, is it always open? No. There are what they call gated channels. And in fact, most channel proteins are gated channels. So they can, given the circumstances, open or close.
Do they kind of act like bullet-worm cells in, like, closed stomata with, like, super stress?
Act like what?
Bullet-worm cells
Okay.
around the stomata with their, like, the big bumpy.
Well, these are so much smaller
Okay.
than a cell. This is something way much smaller.
Okay.
And most channel proteins, both ones that are there, actually have gates. And what does a gate mean? It means if there are certain conditions on the outside that, remember, everything is three-dimensional. You have all those, use my fingers, you've got all those side groups sticking there, and they move some way, and then they can close. So if there's plenty of whatever's going to be transported in on the inside, they can actually close off and stop movement through the channel. And aquaporons, I think in your book there's a good discussion of the aquaporons being gated channels. Okay, facultative diffusion, always down a concentration gradient, can be either direction, and it has either carrier proteins, as we talked, or channel proteins. Pumps, then, are these things. So with pumps, we can move something across or up the concentration gradient. So if these, in almost all cases then, we're moving something from a higher concentration to a lower concentration. In the case of these ATP pumps, they can move something not just not just down the but also up. So there can be plenty more of this compound here, and this can still push more in. And so the only way you can do that, the only way you can move a mineral, anything from a higher concentration to a lower concentration, is energy. If you don't have energy, that can't happen. So that's the purpose of the ATP. So one thing that we can look at, and has been looked at a long time, is what should be the accumulation ratio. In fact, what is the ratio of the plant concentration to soil concentration? Let's look at these, okay? CI versus CO. In this case, this is outside and this is inside. So if we look at potassium, we get a ratio of inside to outside of over 1,000. Sodium, we have something 0.51 on the outside, we get 0.6 on the inside. Nitrate, we have outside a concentration of 0.13. Inside, we can measure a concentration of 38. That's quite a difference. And the same with sulfite, or sulfur, 0.61 to 14. And so you look at these numbers, and so you think right here, if this is moving just by simple diffusion, then what's inside should be what's outside, and that's pretty close. We get a value of 1.18. So for sodium, and in fact we're going to see this is actually different, looks like sodium is moving through the membrane without any assistance whatsoever. So the concentration of sodium outside the membrane, in this, and I think this is P root, I could be wrong, is what we would expect. So you can see by doing these experiments, by putting plant roots in solutions of sodium, potassium, whatever, nitrogen, pulling them out, washing them off, and grinding them up, we can say, okay, we had X amount in the hydroponic solution, and I get 10x the amount inside the plant. So this plant is in some way, shape, or form pulling these minerals inside. Or it could be the opposite. Some minerals are excluded. So a lot of salts are actually in some plants are excluded. You get the point here? And plants do some tricks to move things in the cells. One thing that's very important that you start understanding, and we're going to get this again in respiration, is what is this electrochemical gradient? That is, the membrane at any given time has more positives on one side, which makes the other side negative, right? I don't have to have more negatives on one side and more positives on the other side to make it negative and positive. Or it could be more negative on one side. And it turns out that the membrane really, really, really responds, and most things that are inside the cell and outside the cells have a charge on them, right? Nothing's just neutral. So the cell can be, by electrochemically changing its value, if it's incredibly positive on the inside, that's going to cause negatively charged things from the outside to come inside, right? You got a bunch of positives on one side, then negatives are going to come in from the other side, okay? And this electrochemical gradient, due to the buildup of compounds on one side or the other of the membrane, produces this transmembrane potential, which is the charge across the membrane. And a lot of people measure this. We can actually measure this. Okay? Oh, goodness, look, this membrane's a lot more positive inside than it is outside, or more negative inside. Okay? So let me show you how this works. Here's a real world case. If you look on the outside, you have low potassium. And in fact, the potassium concentration is less on the outside than in the inside. And if you look at each of these little potassium atoms have a K plus. But even under these circumstances, potassium tends to move inside. Okay? So it's moving in some instances against the concentration gradient. And I've put a red circle around why this happens. That's because this protein molecule has a lot of carboxylic acids attached to it, right? And they are, of course, negative. Does that make sense to you? Understand that? So if you look at all those carboxylic acids and you look at those potassiums, inside the cell is negative. The total electrochemical gradient is negative. Okay? So the potassiums can move in. So you're not just taking the entire reading of each individual mineral, you're also taking into account the proteins being negative. Some proteins are made for no other reason than to keep the electrochemical gradient negative inside the cell. Okay? Pretty slick, actually. They're still going to move in and out, but you're still going to get potassium moved in. Okay, here's these electrochemical gradients in pea roots and in oat root. Let's just do a couple of them here. So for potassium, we expect 74, we get 75, so probably potassium moves through by diffusion. Let's look at the next one, which is really important. We have sodium. We put it in this concentration. We predict this concentration. So we should get 74, and we get 8. So what's going on there? I'm predicting that there should be 74 inside, but I'm only getting on 8. So what's going on? Well, what's happening? I'm sorry? I couldn't hear you still.
Is the inside positive?
Inside positive could be. The point is that is sodium good for plants? If I water plants with sodium chloride, salt, then you're right. It has to do with the positivity, the electronegativity. Sodium is excluded. And in the case of both pea and oat roots, sodium is not good. So sodium chloride is not a good thing to grow plants in, right? Then we look at others. We can look at calcium. You get the same thing. Look down at nitrate. In O3, we predict 0.027. We get 28, which means the actual of the predicted is over 1,000. So probably plants have figured out a mechanism to take nitrogen up, which really which really makes total sense, right? I mean, that's the number one thing, the number one inorganic mineral molecule is nitrogen that the plants need. You know, and like for one nitrogen molecule, the plant needs like 0.001 of all other minerals put together. Because we need to produce a tremendous number of amino acids to make proteins, or otherwise nothing gets done. Okay, so you can play these, you can do these experiments, and you can see then over the right-hand column we have diffusion. Then on the question mark there, number 2, diffusion, question mark, because it turns out in different plants we have different mechanisms. Isn't that weird? So we have a pea root that has a different mechanism than a oat root. Overall, they're generally the same. For nitrogen, things like that. And then E means exclusion and U means uptake. So for most of the things, and this is the take-home message that I've told you back from probably day one, is that most minerals follow that Michaelis-Menten curve, the V versus S curve, because transport proteins are enzymes, they don't change it, they don't produce a product, that they grab that mineral and pop it across the cell membrane, so it has the same, it doesn't have a product. The product is what you started with. Nitrate goes over to nitrate, but we're limited by the number of those integral membrane proteins in the membrane. That's going to determine how fast we can move things across. Same thing. Okay, questions? Okay, let's add some more terms. This ATPase that I've showed you establishes a proton motive force. What does that mean? What's proton? Anybody know what a proton is? Proton? A proton's a proton. What about what's motive? Sort of movement. A proton movement force. So the ATPases put protons one side or the other, and then if I push a proton onto one side of the membrane, that makes that membrane positive on that side, and at the same time it makes the other side negative just based on looking at where the positives and the negatives are. Okay? So if you punch out protons to one side of the membrane, which are positives, right? Then the other side's negative. Okay? Because you just don't have protons. Inside you've got organic acids. You've got amino acids. You've got all these negative charges. So if I start making one side positive, the other side then is negative, just by definition. Okay? It is a uniport. In other words, it doesn't pump things both ways. And it is electrogenic because it keeps this charge across the membrane. So in terms of moving things, we've got this cell that's as big as this room. And then if I go up and I put a piece of saran wrap against the wall here, I've got the cell membrane, and then embedded in that cell membrane are all of these wonderful integral membrane proteins, and a lot of them are ATPases, and their purpose is to hydrolyze ATP and to put the proton into the cell wall, which makes that more positive, okay? And that drives a lot. Now let's talk about some very specific cases. What's cotransport? Cotransport means when that proton is moved one way, something else at the same time might be moved the opposite way. And so think of an integral membrane protein. Think of the ATPase. Moves a proton out, moves something in at the same time. Or you can have a condition where it moves something in and something else moves in. They're required to be carried at the same time. And these are defined by what we call antiports and symports. So if it's a symport, then the proton and the mineral is moved in the same direction. Let's say from outside to inside. And an anti is opposite. So with an antiport, and there's 20 or 30 of these in plant cells, with an antiport, you move a proton out, you move what you want inside. Anti. Okay, does that make sense? Anti, so that's very easy to remember. Antiport moves a proton one direction and your mineral in the other direction. Symport transports both of them in the same direction. And here's just a few of them, okay, from your book. Here we have a ATPase that's pumping protons to the outside of the membrane, which lowers the pH. Here we have a gated protein where C plus is moving in. Here we have an example of when a proton is moved into the membrane, we have a C plus, a cation plus moved out. So in this case, we're exchanging a plus for a plus, which is cool. We want to stay neutral. And now we have a condition where we move a proton in and we move a negative in this symport so that maintains neutrality, right? You move a plus in and you move a negative in. Plus and a negative equals 0. Okay? And there's another figure I may put up for you to look at. So you see you have all of these membrane proteins that move things around, then we can have them in the vacuole. Here we have an actual anion being pumped into the vacuole, and here we have another example of proton going out and a positive going in. So remember, you've got the balloon inside the balloon. So you have the cell membrane, and then you have the tonoplast membrane. And they are constantly moving ions around. You know, if we want to get rid of an ion that's dangerous, let's pull it into the vacuole. Once it's inside the vacuole, we're okay with it. Nothing goes on in there. Okay, depends on the plant. I can't look at a C3 or C4, or I can't look at a plant and say, yep, the way that plant handles high salt is it actually pumps the high salt into the tonoplast, into the vacuole, where it's no longer part of the equation in terms of electronegativity or making the cell work. I can't look at a plant and tell you that. That's a plant-by-plant basis. And what we usually do is we go and we find plants that are growing in environments that are high in salt. Because evolution has already developed the mechanism they're using. Right? And so if we understand how this halophyte, everybody knows what a halophyte is, right? Halophyte, high salt plant. Then maybe if we understand this mechanism, then maybe down the road we can genetically engineer a plant to live in that same environment. In all actuality, we probably just shouldn't be growing plants that are in areas that are really high in salt. We can do something else with that land. No. But that's the underlying way we do this. If we find a plant that's growing in a high salt environment, maybe we want to figure that out. Or if we're a breeder like Dr. Pike used to be years ago, plant 100,000 onion plants and expose them to salt water, not a lot of salt, a little bit of salt water, and see if any of them live. And if you see some of them that don't die as quick as the others, well, maybe you can take that plant, cross that into another plant, and maybe you can make a salt-tolerant plant. Or a more salt-tolerant. It's really hard to go out to the desert and pick one of those plants and think in a million years you're ever going to find data that will let you make a soybean salt tolerant or drought tolerant or whatever. You start looking at these plants, they look totally different, right? They're just not normal happy plants that will grow in a high salt environment. Their leaves are different. They're going to have much more waxy leaves so that their leaves are still absorbing sunlight when the water potential is too low. There's a lot of things that are different with those plants. There's no real reason to study cacti because they're efficient at storing water and thinking in any way, shape, or form you're going to put that into a tomato plant. That ain't going to happen. You might get a little bit, but no, there's too many differences between these plants. Okay, questions? Okay, here's something. Let me see what the next slide is. Let me finish on this one. No, I'm going to finish on this one. Okay. So there's something that's more of a newer type thing, which is called crosstalk, which means you can be looking at, you can have your sophisticated hydroponic system where I'm deficient in whatever mineral it is, and I start seeing something funny. And that's because showing you how these things work. Let me go back here. That sometimes, so if I have a deficiency, sometimes, and maybe I'm deficient in the A, this anion, well, maybe another anion will be pulled in, okay? Because of the electronegativity. So maybe another, whatever ion has a -1. So we're finding more and more that sometimes if we grow plants with a deficiency in one mineral, then we'll actually get an increase in another mineral being taken up. Crosstalk. That's because maybe that mineral has a +1, and then the mineral we've removed, so we can do the fancy experiments, has a +1. Well, it turns out that maybe other +1s will also move in more. Makes it much harder and harder and harder to study the absolute conditions we get with a single mineral deficiency. And the people that study mineral deficiencies, they're like, I have a good friend who's the head programmer for Home Depot. For the launch, he's not a programmer. He finds the problems in the programs. Okay, so if I say, is it daylight or dark? He's going to go outside and look first because he's that kind of a guy. Okay, OCD like crazy. Nothing is taken. It's hard to talk to him sometimes. And the people that do these mineral experiments are pretty much the same. This is a really hard thing to do. Okay, so now I find if I don't give the plants nitrogen, then they may get a deficiency in some other mineral, or they may get a toxicity in another mineral. So nitrogen deficiency symptoms turn out to be toxicity deficiencies of something else. You know, because the membrane says, I need to move a positive across, let me move a positive across. Membrane says, I need to move a negative across, let me move a negative across. Does that make sense? Okay? See you Wednesday. Anything else? Man.